Okay, so let's do our second example here where we do a conversion using the Jacobian. And we're going to do this double integral using the conversions that u will be equal to x plus 2y and v will be equal to y minus x. So of course there's three steps to this. The first step is we've got to take the equation x plus 2y e to the y minus x and convert it over. And this looks like a very simple conversion because I can see that x plus 2y is going to be u. And then I have e raised to the y minus x, which is v. So our first conversion is done quite simply. The second part of this is to calculate the Jacobian, and remember this is the determinant of the matrix, which has across the first row the partial of x with respect to u, then the partial of x with respect to v. Second row will have the partial of y with respect to u, and then the partial of y with respect to v. And of course, to do this, remember I said what you need is you need an x equal function and you need a y equal function. But that's not what we're given here. What we're given here instead is a u equal and a v equal. So let's see if we can take that u equal x plus 2y and the v equal to minus x plus y and solve these for both x and y. Now to do that, we have several options on this. We can just come in and do a substitution where I solve one of them for one of the variables and put it in the other. Or in this case, it lends itself quite nicely to just a simple elimination. If I go ahead and add these just like they are, I see that the x disappears and I get u plus v will be equal to 3y. So then y is going to be equal to, multiplying through by 1/3 u plus 1/3 v. Now I can take that and I can substitute that back into either one of these two equations to, actually I need to substitute it, yeah, I can do it into either one to solve for the other variable. And I can do that right here. So everywhere there's y, I'm going to put in the 1/3 u plus 1/3 v. So I've got v is equal to a negative x plus y, and then we'll put this in for y. So v is going to be a negative x plus 1/3 u plus 1/3 v. Let me go ahead and move the x over to the left-hand side, which will make it positive. And then I'll move the v over to the right-hand side. So that's going to give me 1/3 u. And then 1/3 minus 1 is going to give me a negative 2/3 v. So here and now I have what I need to calculate my Jacobian. And so my Jacobian then is going to be the determinant of the matrix, which has the partial with respect of x with respect to u, which is 1/3, partial of x with respect to v, which is a negative 2/3. Then we'll use our y equation. We'll take the partial of y with respect to u, which is 1/3, and the partial of y with respect to v, which is 1/3. And then remember, we multiply in this direction. 1/3 times 1/3 is 1/9. And then we subtract what happens when we multiply in the other direction, which is going to be actually a negative 2/9. That gives me 3/9, or just a simple 1/3. So we now have our Jacobian. The last and final part of this is to take the bounded region. And to determine our bounded region, of course, what we're going to do is we're going to go back to our original equations here, or original integral here, and remember how this works. The outer bounds are bounds on y. So what I can see here based on this is that y has to sit between 0 and 1. And then the inner bounds are bounds on x. So x has to sit between y and 3 minus 2y. So let's see what that actually is going to look like then. That gives us actually four equations. That gives us y equals 0, y equal 1. That gives us x equal to y and x equal to 3 minus 2y. And this is real easy to do here because to find out where these things intersect, I simply need to take one of the values, solve it for one of the equations, it's already done, and then go ahead and plug that into both of these. So when y is equal to 0 here, I simply plug in the 0 into this first equation, which tells me that x will be equal to 0. And then I'll plug in the 0 for y into this equation, which tells me that x is equal to 3. I'm then going to repeat the process here using y equal to 1. So when y is equal to 1 and I plug it into this equation, I get 1. And when I plug the 1 into this equation, I also get 1. So we just get a repeated section there. But these are then the x, y coordinates that I need to switch over to u, v coordinates. So I've got 0, 0, 3, 0, and 1, 1. And we were given, this is where we're going to need the u equal and the v equal. U was equal to x plus 2y, and v was equal to y minus x. So again, I like to do all my u's and then all my v's. So x plus 2y is 0. 3 plus 2 times 0 is 3. And 3 plus 2 times, 1 plus 2 times 1 is also 3. My v is y minus x. 0 minus 0 is 0. 0 minus 3 is a negative 3, and 1 minus 1 is 0. So we can go ahead and graph our UV region here. And it looks like that we are going to be bound, or our points of intersection are these. So we've got 0, 0. We've got 1, 2, 3, 0. And we have negative 1, excuse me, positive 3, negative 3, excuse me. So this actually looks like our bounded region. So we should have enough then to do our integral. So remember what this looks like. Going back here, we rewrote our function as u e to the v, and we have our Jacobian. So we are going to rewrite our function of x and y dA as the double integral over our new region of our new function written in terms of u and v times the absolute value of the Jacobian. And then we can either do a du dv or a dv du. So this is going to be the double integral, and we rewrote our function as u e to the v. Our Jacobian was 1/3, and so the absolute value of 1/3 is 1/3. Don't forget to always take it as an absolute value. And then I have a choice here whether I choose to do a du dv or a dv du. And the choice is completely up to you. If I were to do, for example, a dv du, v's coming down from the top. So as I come down from the top, I hit v equal 0. And then I come down and I hit this line. Well, what is the equation of this line? Well, we got to figure that out. It passes through the point where u is 0, v is 0, and the point 3, negative 3. You can find the slope then will be negative 3 minus 0 over 3 minus 0, or negative 1. Then using y minus y1 equals m times x minus x1, and I will use the ordered pair 0, 0. I get y minus 0 is equal to negative 1 times x. I'm sorry, and I'm using x's and y's. This should be v minus v1 and u minus u1. So I get v minus 0 is equal to negative 1 times u minus 0, or v is equal to a negative u. Okay. Okay, so let's go ahead and write this up then. So v then is going to go from 0 to negative u. Then for my du, I will grab my bounded region and drag it over to the u-axis, and I am bound from 0 to 3. And so this would be the integral that you would then go through and integrate.